Hello everyone, welcome back to ch205. This is the next section on solving the differential equations numerically. So last time we left off at section 5.2.5 of the textbook. Today we're going to talk about the accuracy of Euler's method, the forward and the backward difference, as well as the trapezoidal rule. Okay, so to consider the accuracy of a numerical technique, what we have to do is we have to use Taylor series and expand the approximation and see at what point the expansion deviates from the exact solution. So let's start from Euler's method, the forward difference with the toy problem we looked at before, to look at the stability analysis, right? So for the stability analysis, if you remember, we started from an equation which was y prime equals minus a times y, right? So we look at this with the given initial condition. We know the solution to this system is exponential of minus at, right? Okay, so with this in mind, we're going to go in and look at the expansion of forward difference using Taylor series and compare it with the exact solution. Okay, so remember that when we expand or discretize the differential equation using forward difference, we got equation 5.9, in which yn plus 1 is equal to 1 minus a times h, which is delta t times the previous y value. Okay, so we're going to go back here and start off by changing this equation a little bit. So if this is the exact solution, I can say that yn plus 1, let me just write it down here. Okay, so if this is the exact solution for the toy problem we looked at, then let's say n plus 1 this is equal to exponential of minus a times t n plus 1, right? So this is by definition. So I'm going to expand t n plus 1. So t n plus 1 is tn, right, plus dt. That's what we mean by tn plus 1, okay? All right, so next is, so I'm going to expand the exponential. So this is going to be exponential of minus a times tn, and then times exponential of minus a times dt. All right, and we know that dt, according to the textbook notation, that's going to be h, so I'm going to write it as h. And let's compare this last equation that I have here with this one. So, okay, so if you compare the last part of the equation that I wrote with this one, you can see that yn plus 1 is equal to, this one is yn, right? Because if this is yn plus 1, which is at tn plus 1, then same expression at tn is going to be yn. So this is yn. So that is equal to yn plus 1 equals yn times exponential of minus at. So far we haven't changed anything. This is still the exact solution. Okay, so now we're going to expand this exponential using Taylor series. So Taylor series of that is going to be, you can look it up maybe on internet or any mathematical handbook you have. The Taylor series in that is going to be 1 minus ah plus 1/2 ah squared minus 1 over 6 and the rest of it. Okay, so the parentheses here is the expansion, the Taylor series expansion of the exponential. Okay, so let's leave this here and then go back to forward difference. So in forward difference or forward Euler, we had this expression. Okay, and in forward difference, you can go back and double check. So the equation for forward difference was yn plus 1 is equal to 1 minus h times yn. So we're going to repeat that over here and compare it with the exact solution we just found. So this is forward difference. This is exact solution. So let's do a comparison. So the left side is the same. The right side, 1 minus h times yn is over here. And looks like the rest of it is truncated. Okay, so the truncated term starts with 1/2 ah squared. So we say the error that we're making is from this point on, and the highest power is, or actually the lowest power. The lowest power is the largest portion of the error. Okay, and the reason is because h, we assume that h is a small, and if a small number raised to higher power gets a smaller. So the largest portion among all these terms would be the first term, which is ah squared. So we can say the order of the error is h squared, or its second order. But this is just the relation between yn plus 1 and yn. And we have to go all the way to find a relation between yn plus 1 and y0. Because we know y0, we don't know any other y's. So we have to relate y0 to y1, and then y1 to y2, and y2 to 3, and so forth, until we get to yn plus 1. So at every relation between two successive y values, the error we're making is on the order of h squared. Okay? And because of that, if you just look at the global error, which is the accumulation of error over all relations, so the error is on the order of h. So the error actually goes bigger. Okay? So don't think that the power goes down, the error goes also down. No. Because h is a small, as the power of h goes down, the total error actually goes up. Okay? Because h is usually small, it's less than 1. So any number less than 1, as you raise it to higher power, actually becomes smaller. And inversely, if you have a number less than 1, you raise it to a small number, as you lower the exponent of a number less than 1, then the result actually goes up. That's why at every relation the error is on the order of h squared, the global error is on the order of h. The error goes up by a factor of h because that's the global. Okay? Alright, so the forward Euler is on the order of h according to the Taylor series. Now we can look at backward difference. In backward difference, if you remember, we had this relation. So let's go back. Here's backward difference. And that's the equation we derived. Right? The relation between two successive y values is like 1 over 1 plus ah times yn. And now we want to compare this equation with 5.16, because 5.16 is the reference, is the accurate solution, is the exact solution. Okay, so now we're going to expand this fraction using Taylor series. So using Taylor series, this is going to be 1 minus ah. I'm just expanding this fraction, or this ratio. Okay, so it's minus ah plus ah squared minus the rest of it. Okay, let's compare 517 and 516. So the first term is the same, right? 1, 1. Ah is the same. The third term is different. So here we have ah squared. Here we have ah squared divided by 2. So this is the error we're making, and from this point on would be the total error. Now the smallest power in error would be the local error, which we call it OH squared, because at the h squared we're making a difference. We're making a difference with the exact solution. Okay, so the local error is on the order of 2. That means the global error is on the order of 1. So that means it's OH. Okay, so the global error for backward difference still is OH. Again, to remind you, what OH means is if you lower h by a factor of 10, the error goes down by a factor of 10. It's linear with respect to h, basically, or with respect to delta x, or in this case, delta t. Okay, now finally we're going to look at trapezoidal rule and see what the error here is. Now, trapezoidal rule, if you remember, we got an equation like this to iterate. Yn plus 1 is 1 minus h over 2 over 1 plus h over 2. Okay, and now we just expand this fraction of this ratio to be able to compare with the exact solution. So if you expand this using Taylor series, we get 1 minus h. 1 minus ah plus 1/2 h is ah squared minus 1/4 ah cubed, and so forth. Now let's compare 518 with the exact solution, which is 516. Okay, so the first term is the same, right? 1, 1. The second term is ah. We have ah here. The third term is 1/2 ah squared. We have 1/2 ah squared. I think this is misplaced. This should be outside the parentheses. Okay, so that's a typo. And then the fourth term is 1 minus 1 over ah cubed, but here is 1 minus 1 over 6 times ah cubed. Okay, so if you compare, you see that the error is on the order of, the local error is on the order of oh cubed, or is on the order of h cubed. That's the local error, so the global error would be h squared. So same thing divided by another h. So the global error here for trapezoidal rule is oh squared. So compare that with backward and forward difference. So the error actually here is lower. This is more accurate, right? Which means if you lower your h by a factor of 10, in trapezoidal rule, the error that you're making in the solution of the numerical solution of the differential equation is going down by a factor of 100, in contrast to the error we're making in the solution using forward or backward difference, which goes down by a factor of 10. Right? So here it goes by a factor of 10 because that's what we here the error goes by a factor of 100. So that means we more rapidly get to the exact solution, or closer to the exact solution, using trapezoidal rule. Okay, I hope this is clear. I think that was a short discussion on the accuracy of Euler, the forward Euler, backward Euler, and trapezoidal rule, where we use finite difference to compare with the exact solution. We use finite difference, of course, as well as Taylor series to be able to compare with the exact solution. Okay, so I'm going to stop here. In the next video, I'll be talking about a fourth technique to do the differential equations numerically. So far we learned forward, backward Euler, trapezoidal rule, and then in the next video we're going to look at the Runge-Kutta methods, or RK methods. Okay, so stay tuned and thanks for watching.